black holes get all the attention. They're mysterious, invisible, and dramatic. But there's another class of object in the universe that is almost as extreme, far more tangible, and in some ways even stranger. Neutron stars. These are the dead cores of massive stars that went supernova. They are tiny, just a few kilometers across, and yet they contain more mass than an entire star like our Sun. A neutron star is so dense that a single teaspoon of its material would weigh billions of tons. The gravity on its surface is billions of times stronger than Earth's. It spins hundreds of times per second, beams radiation across the cosmos, and can warp space-time around it almost as much as a black hole. Today, we're going to explore these incredible objects, how they form, what they're made of, and why they are the densest objects in the universe that we can actually observe. The birth of a monster. Neutron stars are born from death. When a star between about 8 and 20 times the mass of the Sun runs out of fuel, its core collapses under its own gravity. The outer layers of the star are blasted away in a spectacular supernova explosion, briefly outshining an entire galaxy. What remains is the core, a ball of matter so compressed that protons and electrons are crushed together into neutrons. The result is an object about 20 kilometers in diameter, but with a mass of 1.4 to 2 times that of the Sun. To put that in perspective, imagine squeezing the entire mass of our Sun into a sphere the size of a city. That's a neutron star. The matter inside is so dense that it exists in a state we cannot create in any laboratory on Earth. It's the closest thing to a single, giant atomic nucleus. A teaspoon that would crush a mountain. Let's really understand the density. The average density of a neutron star is about 10 to the power of 17 kilograms per cubic meter. That's 100 trillion times denser than water. A single teaspoon of neutron star material, about 5 milliliters, would have a mass of roughly 10 billion tons. That's the weight of a mountain, compressed into a volume smaller than your thumb. If you tried to bring a teaspoon of neutron star material to Earth, it would immediately explode outward because the gravity holding it together is gone. But if you could somehow keep it compressed, it would punch straight through the planet like a hot knife through butter, carving a tunnel to the other side. Nothing we know of can withstand that kind of density. It's matter pushed to its absolute limit. A world of extremes. The gravity on the surface of a neutron star is beyond imagination. It's about 2 billion times stronger than Earth's gravity. If you dropped an object from a height of 1 meter, it would hit the surface at millions of kilometers per hour in a fraction of a second. The escape velocity is about half the speed of light. To leave a neutron star, you would have to fire a rocket at 150,000 kilometers per second. The surface itself is not solid in the way we think. It's a crust of iron and other heavy elements, but under immense pressure. The crust is likely smoother than any surface in the solar system. The gravity flattens any irregularities. And the temperature is extreme. A newborn neutron star can have a surface temperature of 1,000,000 degrees. Even older neutron stars are still hundreds of thousands of degrees hot. Cosmic lighthouses. Neutron stars spin. They spin incredibly fast. When the core of a star collapses, it conserves angular momentum, like an ice skater pulling in their arms. A star that took weeks to rotate can end up as a neutron star that spins hundreds of times per second. The fastest known neutron star, PSRJ 1748-2446 AD, spins at 716 revolutions per second. That's 43,000 times per minute. As they spin, neutron stars emit beams of radiation from their magnetic poles. If those beams sweep across Earth, we detect a pulse of radiation with every rotation. These objects are called pulsars. They are so regular that some pulsars rival atomic clocks in their precision. In fact, when the first pulsar was discovered in 1967, astronomers briefly nicknamed it LGM-1 for Little Green Men because the signal was so regular they thought it might be artificial. The strongest in the universe. Neutron stars have magnetic fields that are incomprehensibly strong. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. But some neutron stars, called magnetars, have fields 1,000 times stronger than that, up to 100 trillion Tesla. For comparison, Earth's magnetic field is about 0.00005 Tesla. A magnetar's field is so strong that it would strip the information from your credit card from halfway to the moon. Magnetars are rare and violent. They produce gigantic flares that can outshine entire galaxies for a fraction of a second. In 2004, a flare from a magnetar called SGR-1806-20 was so powerful that it ionized Earth's upper atmosphere from 50,000 light-years away. If such a flare happened within a few light-years of Earth, it would strip away our ozone layer and cause mass extinction. Fortunately, there are no magnetars that close. The unknown core. What lies beneath the crust of a neutron star? This is one of the great mysteries of modern astrophysics. The outer layers are thought to be a lattice of iron nuclei, but deeper down, the pressure becomes so extreme that matter breaks down into exotic states. There might be a nuclear pasta phase where atomic nuclei squish into spaghetti-like or lasagna-like shapes. Deeper still, the neutrons may become a superfluid, a liquid that flows without friction. And at the very center, some models suggest a core of deconfined quarks, a soup of up, down, and strange quarks floating freely, not bound into neutrons. These hypothetical objects are called quark stars. We don't know if they exist. The only way to find out is to measure the mass and radius of neutron stars with extreme precision. Missions like NASA's NICER, mounted on the International Space Station, are doing exactly that. From radio to gravitational waves. We can't see neutron stars directly with telescopes. They're too small and too dim, but we can observe them through their pulsar beams, through X-rays emitted from their hot surfaces, and through their effects on companion stars. Some neutron stars are in binary systems, pulling gas from a normal star. That gas heats up and emits X-rays, making the neutron star visible to X-ray telescopes like Chandra and XMM Newton. And now, we have a new way to study them: gravitational waves. In 2017, LIGO and Virgo detected a neutron star merger. Two neutron stars spiraling into each other, creating ripples in space-time. The event, GW170817, was also observed across the electromagnetic spectrum, from gamma rays to radio. It confirmed that neutron star mergers produce heavy elements like gold and platinum. It was one of the most significant astronomical events of the century. The universe's extreme frontier. Neutron stars are the densest objects we can directly observe. They push matter to its limits, creating conditions that we cannot replicate on Earth. They are natural laboratories for nuclear physics, general relativity, and quantum mechanics. Every new observation, whether from radio telescopes, X-ray satellites, or gravitational wave detectors, teaches us something new about how matter behaves under the most extreme pressures imaginable, and they're beautiful in a violent way. Spinning pulsars, explosive magnetars, merging binaries, these are not static objects. They are dynamic, changing, and sometimes deadly. They remind us that the universe is not a gentle place, but they also remind us that we live in a time when we can finally begin to understand it. What fascinates you most about neutron stars? Their insane density, their spinning, or their role as cosmic forges for heavy elements? Let me know in the comments. Thanks for watching Daily Dose of Space. Stay curious, and I'll see you tomorrow.